Hello and welcome to a last video on the additional effects for the Jeffcott rotor. A much shorter video than the previous one. However, I can't promise that it's less difficult to grasp. Well, what I would like to study is the inclination of the disc. So the last subject on that line. What's so special with discussing the inclination of the disc? Let's look at the situation. Here you can find a disc. You can see that the disc is not located to the middle of the shaft. It could be there, but it indicates a typical situation where the inclination of the disc might have an effect. It's namely for so-called overhang rotors. So you have the two bearings here, and then overhang rotor means at the very end, so opposite to these two bearings, there is the disc. And you can see that there is another coordinate system, x prime, y prime, z prime. This coordinate system refers to the principal axis for the mass moment of inertia of that disc. And now you can see that the disc is slanted, that is, it's inclined. The coordinate system x prime, y prime, z prime of these principal axis is rotated with respect to our space-fixed coordinate system x, y, z. So we have in total 4 degrees of freedom. The classical 2 degrees of freedom describe the bending vibrations. The other 2 degrees of freedom describe the inclination of the shaft, and therefore the angles phi sub w and phi sub z. So the first question is, where does this matter? And of course this matters for the inertia term and for the moment of inertia tensor, so for the mass moment of inertia. We will assume that our disk has a rotational symmetry. So represented in the principal coordinates of that mass moment of inertia tensor, we will find 3 entries, the entries of the diagonal. 2 entries are the same, they represent the axial mass moment of inertia, and 1 entry is then the polar mass moment of inertia. This is then the equation for phi, for the mass moment of inertia tensor. When it comes to the angular momentum, you obtain the angular momentum by multiplying phi with the vector of rotational velocities. The rotational velocities in x direction is omega. The rotational velocity in the y and z prime direction would be phi dot y sub w and phi dot y z. Well, as this would be the result in principal axis, but we want to still formulate our equations of motion in the space-fixed coordinates, we have to transform this result, so from principal axis to space-fixed coordinates. So that transformation is done in 2 steps. In a first step, we rotate our coordinate system from x and z coordinates to x sub 1 and z sub 1 coordinates by rotating around the y-axis. The amount we rotate around the y-axis is given by the angle phi sub y. The relations for the unit vectors are obtained by projecting them on the x and z axis. This is done for x sub 1 by taking the cosine of phi in the x direction minus, as the z-axis points downwards, minus the sine of phi times the ez unit vector. And this equation can be simplified if we assume small inclination angles. That's what we will assume here. And what's also very realistic, then it can be simplified by setting the cosine to 1 and the sine to -1. we treat in the same way the second unit vector E sub z1 of the newly obtained coordinate system. And it's then E sub x times the sine of phi w in y direction and Ez cosine of phi. So this contribution here, Ez cosine of phi wy. And now again we simplify, so we linearize that relationship for small inclination angles phi y. So you can see that you replace again the sine function by the argument, so Ex times phi wy, and then it's just Ez because the cosine is equal then close to 1. Second transformation, which now turns our intermediate coordinate system x1 and z1 and y1 into the final destination, so the final coordinate system x prime, y prime, z prime. So into our coordinate system of principal axis. It's a rotation around the z-axis, so around z prime equal to z1 by an amount of phi index z, and that rotation is then leads then to finally to the principal axis ax prime, which is ax1 times the cosine of that angle, so this contribution here, plus the contribution in y direction, ey sine phi wz. And finally, we can also linearize that expression and insert for ex1, our intermediate unit vector, the space-fixed unit vectors ex minus ez phi wy, and we linearized the contribution from the sine function by ey phi wz. The last one, which is still missing, is then ey prime, and ey prime because ez prime is already obtained here. For ey prime we have minus ex1 sine phi wz, so it's the contribution for ey prime in opposite to the x direction by an amount of angle phi, and plus ey cosine of phi. And again we linearize that expression to yield minus ex phi wz plus e sub y. So that's the technical part, I would say, doing all these transformations. So when we summarize these results, we will find the transformations between the space-fixed coordinates and our principal coordinates, and they are summarized here again, and it's an approximation because we linearize the dependence here. So having these three equations, we start by inserting the principal coordinates for the angular momentum. Here we write down our angular momentum vector in principal coordinates. This is the starting points because only for this angular momentum we have the values computed with the mass moment of inertia tensor at hand that you saw on the previous slides. And then we insert this relationship here to obtain the contributions in space-fixed coordinates. And then we assemble all the terms, so the terms belonging to Ex, but they are not of importance for us because we are dealing with the bending vibrations, not with the question, is there a stationary state or not? So we do not deal with the case that we consider the momentum balance with respect to the x-axis, but we are interested in the y and z contributions. And you can see these y and z contributions, I will summarize them here. So this would be the angular momentum in y direction, space-fixed y direction. It's composed, where do we have it? Ly prime times Ey is the main contribution, I would say. And then there is a second contribution from Lx prime. It's Lx prime times phi wz. For Ez, we have Lz being equal to first contribution, largest contribution will certainly be Lz prime. And then we have another contribution coming from, here is it, Lx prime phi Wy with a negative sign. Now for Ly prime, Lx prime and Lz prime, we can insert our values that include now the mass moment of inertia in axial and in polar direction and the corresponding angles. And the good thing is that for our coordinates, we obtain linear terms. The only, one could say, non-linearity is related to the rotational speed, but keep in mind the rotational speed, we are always dealing with a stationary operation, so the rotational speed of our rotor shall be given. So this is the contribution on the inertia part. The second contribution for the inertia part, that is of course also there, is that from the linear momentum, but this is known to you because this is the same as for the classical Jeffcott rotor. However, when it comes to the restoring forces, we also have a difference. Namely, we have to take into account the restoring forces now also for the inclinations. But let me first, in the first step, use these expressions, the so-called linearized, because we do not use sine and cosine functions here, linearized angular momentum, and take the first order derivative in order to be able to formulate the balance of angular momentum here. So the linearized angular momentum is given here. It's copied from the slide before, and now take the derivative of this expression with respect to time in order to apply the angular momentum theorem. So you obtain the second derivative of phi here, and here the first derivative of phi, and you do not get any contribution with the first derivative of omega because we are in stationary case. We assume that our rotational speed is constant. Same for the second equation. You take the second derivative of phi wz and the first derivative of phi wy. Okay. Now let's turn to the stiffness part, and then let's try to assemble the system that we obtain, the system of ordinary differential equations. We are in full bending beam theory. So classical bending beam, Euler-Bernoulli hypothesis, that planes remain plane. We use linear elasticity, and the consequence for the stiffness matrix is that it's symmetric due to the reciprocal theorem of Maxwell and Betti, and it can be obtained by the superposition principle, so by superposing individual load cases. So you apply a force, for example, where the disk sits in vertical direction, you compute the bending, not only the bending, but also the slope of the bending line. And from the slope of the bending line, you will find the contribution, the stiffness contribution to the corresponding inclination angle. You do the same with the force in lateral direction, and you can also apply torques at the position where the disk is in order to get the bending contributions. All this is done for an isotropic cantilever beam. You will arrive at the following stiffness coefficients. So there are always two directions, y and z, and there is one angle included, and this is C1, 2, and you get the following symmetric part of the stiffness matrix. If we then want to assemble the whole matrix, we get the inertial contribution in the second derivative, which comes from the linear momentum and angular momentum theorem. A linear momentum theorem in z and y, so our vector of generalized coordinates here is now composed by z and y and by two angles, phi sub w and phi sub z. In the phi and phi directions, we have the angular momentum theorem. So some entries of the mass matrix first and the third row stem from linear momentum theorem. Second and fourth row stem from angular momentum theorem. The gyroscopic matrix is included here because if you look again at the angular momentum theorem, then you had a first order derivative, first order contributions. So these terms will manifest in the second and the fourth row. And the contributions to the stiffness matrix are two 2x2 matrices related to Z and phi. So in the one plane, and Y and Z, and Y and phi Z in the other plane. So this being said, you get the following contribution. Mass matrix, first row, linear momentum theorem, it's the mass of the disk. Second row, angular momentum theorem, it's the axial mass moment of inertia. Third row, again, linear momentum theorem, it's the mass of the disk. And last row, it's the contribution of the angular momentum theorem. The angular momentum theorem has a contribution, as we derived it, from the polar mass moment of inertia, and that polar mass moment of inertia is then related to the other angle, as you can see here, to the first derivative of the other angle, as we did it in the derivations. So you get omega, rotational speed, times jp, and then the corresponding signs here. And for the stiffness matrix, we have that contribution C sub 11, C sub 12, C sub 12, and C sub 22, which is basically the contribution in the Z and phi plane. Due to unit forces and due to a unit torque, and you get the same contribution. There's just a change in sign because the orientation of the phi angle is different. You get a similar contribution here in the second block of that stiffness matrix. So, and well, the last question, what would be the excitation? Well, if you have a close look at the linear momentum theorem, then you know that you have to apply the linear momentum theorem with respect to the center of gravity. Everything else deals here, the whole vector deals here as before for the classical Jeffcott rotor with coordinates related to the connection point between a shaft and disk. So in order to transfer these second order derivatives in the linear momentum theorem to the connection point between shaft and disk, you have to apply kinematic relationships and you move terms that are independent on the displacements, velocities or accelerations on the right-hand side. So on the right-hand side, vector P, there will be entries related to the first row and to the third row, and they are the classical imbalance effects you already saw for the classical Jeffcott rotor. So it's this one. It's due to the eccentricity of the center of gravity, and it appears in the first row as being me omega squared sine omega t, and it appears in the third row as being me omega squared cosine omega t. That should give you a little bit of flavor of the whole procedure. You see, I'm a little bit fast. I just would like to show you the effects without entering too much into the technical details. So therefore, I switch to the solution procedure. Again, here, there's no danger at all from anything related to the homogeneous equation of motion. Why? Because your mass matrix is really nice. Your gyroscopic matrix introduces a coupling, but the coupling is really the classical coupling of a gyroscopic effect. It's a skew symmetric contribution related to the two angular degrees of freedom. And the stiffness matrix is a classical stiffness matrix here, no special effect. So we will focus on the particular solution. And for the particular solution, we will make a setting. A setting related to the right-hand side, where the only question is it sufficient to have a setting with sine omega t and cosine omega t, instead of having also phase shifts included? And the answer is, which is the good news, it's possible to do it without any phase shift. You can, well, either you go briefly through the equations and look where you will have the coupling and where you will have the sine terms and the cosine terms. But if you apply for the first plane for the z phi y component a sine function, and for the second, because they are coupled here by the stiffness matrix only, which is no problem at all. And for the third and the fourth row, so for y and phi z for the other plan, if you there include the cosine term, then you see the coupling appears again with the first order derivative, where you couple an influence from the other plan to that plan. And as for the other plan, you use the cosine, while for these first plan, you use the sine function by taking the first derivative. You have the same effect as discussed in the video before. You don't need any phase shift here. So this being said, we will use sine functions, sine harmonics for z and phi y for the particular solutions, and for y and phi z we use cosine functions, and we are looking for these amplitudes. We get an algebraic system that governs these amplitudes, and again here's the question, are there critical rotational velocities? And there are, and the expression is quite lengthy, and I don't want to derive it with you. You plug it in, you solve the equation that is obtained there for omega k, and you see it's quite involved. And now the question is, what can you learn from that solution? Well, what you can learn is we are dealing here with critical rotational velocities. The critical rotational velocity must be a real number. There are no imaginary or complex numbers for a rotational speed. There is no complex rotational speed. It's a real number. So once you get something that is not real, so something that is negative in that root, then you know it's not a critical rotational velocity. It does not matter physically, practically, it doesn't matter. So the question is, as there are two signs here, do we always get two critical rotational velocities? This ends a little bit the discussion on several critical velocities, or is there just one critical speed? Well, there is the possibility of having another critical speed, so two positive values for that radicand here, if the second term is less than the first term, as the first contribution of that second term of that square root copies just this term here. The question is, how about that sign of that term? If the sign of this term is negative, then we will have two critical rotational speed. If the sign of this term is positive, then you add something up to this term. So the whole second term with its negative sign will be larger than the first term, and due to the negative sign will lead to a negative radicand, and that negative radicand of course will not lead to a real valued omega k. So then in this case there is just one critical rotational velocity. So what can be said about the sign of this second term here? When is the sign negative? There are two chances to get a negative sign, either from the numerator or from the denominator. For the numerator, the result is in this regard disappointing. Well, if you look at the terms for C11 and C sub 2, then the product of C11 and C sub 2 is always larger than C sub 12 squared. No chance for the numerator to have a negative sign. Then everything amounts to the denominator. And of course, the denominator can be negative or positive. The denominator will be negative if Gp is less than G sub A. It's positive, so we just have one critical speed if Gp is larger than G sub A. Well, what is the case that a polar mass moment of inertia is larger than the axial mass moment of inertia? Well, the mass moment of inertia is always the distribution of the mass close to a disk, close to an axis of rotation. If Gp is larger than G sub A, we have a very thin disk. So very, very thin disk, so that extends laterally in the two directions, but not axially. Therefore, the polar mass moment of inertia is large, the axial mass moment of inertia around these other two symmetry axes and the lateral direction is quite small. The other case would be that Gp is less than G sub A, and in this case we have two critical rotational velocities. Now the axial mass moments of inertia are quite large. The axial mass moment of inertia and the polar mass moment of inertia is quite small. So this would be a cylindrical disk. Yeah? So either we have a thin disk with one critical rotational velocity, or we have a cylindrical disk with two critical rotational velocities if we take the effect of slantedness, so the influence of an inclination of the disk, into account. And this is the final result. You see again that equation here, and the result is for a thin disk there's one critical rotational velocity. It's larger than without taking the gyroscopic effects into account. Without taking the gyroscopic effects into account means we just have the first term, C11 divided by m. And for the second one, for a cylindrical disk, we have two critical rotational velocities. One critical rotational velocity is larger, the other one is lower than the critical velocity you would obtain without any gyroscopic effects. So with this you can estimate the influence of the gyroscopic effects of a slanted, of an inclined disk, whether you are in the case of a thin disk or you are in the case of a cylindrical disk, on the critical velocities. Will it be just increase the critical velocity, so you have to be or keep a little bit more distance if you are in the supercritical range, or will they just be in between? Well, then of course you also have to increase, of course, the distance to the critical velocity that you compute without the gyroscopic effects, and avoid, but of course that should be also done, avoid a certain range around that critical velocity that you obtain without taking gyroscopic effects into account. So this is everything I would like to say about that, the influence of the gyroscopic effects for an inclined disk. There's one last video on the Jeffcott rotor, and in this last video we will now move from the single disk rotor to multi-disk rotors, and at the very end to I would say to a smeared distribution of the mass, so to a continuum model. And the question then is, what happens to the critical speed? How many critical speeds are there for a multi-disk rotor and for a continuum rotor? This question will be answered in the next video. Thank you very much for your attention.